Hello everyone, I'm Rachid Ben Saada from the Interlaminar Research Institute. Within the framework of the 27th International Conference on Fracture and Structural Integrity, I have the honor to present the work entitled Interlaminar Strength Characterization of Tensylon under multimodal loads. This work is a part of the DYNACOM project funded by the French Agence for Innovation in Defense. The field of ballistic protection is subject to significant challenge. The main of them is to decrease the weight of protective devices while improving their structural properties. These reasons make this field in constant evolution, notably by replacing conventional materials as metals and ceramics, partly or fully by composite materials for some obvious reasons that could be deduced from the HB diagram. The UHMWPE composites are known as sacrificial coating. Tensylon, the material of interest, belong to this family. The efficiency of these materials under ballistic impact is proven. However, some improvements are still possible by hybridization or multi-material assembly. The main objective of the present project is the hybridization of Tensylon in order to improve its properties under ballistic impact. To assess the gain obtained by hybridization, the out-of-plane properties of the Tensylon should be evaluated. To do so, we have many options. Among them, we can cite conventional tests as DCB, ENF, and MMB. Unfortunately, these tests are not suitable for our case, given that they require crack initiation. We have also scarf and tast testings. These tests present also some drawbacks as edge effects and complex triaxial stress at high stress gradient zones. To overcome these limitations, we opted to the modified Archon device. Here we give the content of the presentation. We just talk about the context. Now we'll introduce the material of interest, the Tensylon. Here we give a typical UHMWPE composite manufacturing process. It's a three-step process that could permit to obtain the final product by consolidation. We can find within the market four main products. The Tensylon manufactured and provided by DuPont in form of 500 square millimeters flat and two stacking 0.90 and plus or minus 45. Here we give the geometry of the Archon specimen. Within the project, we perform material characterization following three strain rates. Here we just focus on the weakest one, 0.1 millimeter per minute. Here we give some results concerning tensile tests for the two stackings, 0.90 and plus or minus 45. We can notice a good reproducibility of tests. Dissipate an important inhomogeneity in Tensylon. The data obtained from material characterization is used to identify the Ashin damage model, and here we can see a good reproducibility of the experimental test by the finite element analysis. Here we present the Archon device. It consists of two half-moon shaped pieces made of high stiffness steel. Within the device we can find holes that make it possible to test the material following a wide range of stress states. 0 degree can give us tensile loading and 19 shear load. By using intermediate angles, we can apply a combined tensile shear load or a combined compression shear load from 19 to 135. The other particularity of the Archon device is the introduction of peaks within the substrates in order to avoid stress singularities. Concerning the choice of the adhesive, it was challenging given the weak surface energy of Tensylon and its poor thermal properties. Permabond TA4610 acrylic adhesive was selected given its low temperature of curing, about 23 degrees. Other surface treatments were also performed both on the Tensylon surface and the substrate, sandpapering to increase the roughness of the surfaces, and also a corner treatment in order to charge positively both Tensylon and substrate surface in order to increase their surface energy. Concerning the post-treatment, it was done by digital image correlation thanks to the Aramis technology. It consists in measuring the relative displacement of the substrates. The procedure requires also a speckled pattern applied on one side of the substrates. It's the side in the front of the camera. Concerning the substrate choice, it was done thanks to the pull-off testing in accordance to the ISTM C633 test. This test makes it possible to do the choice of the ABS. That's the only one that gives us a cohesive fracture in all the cases. While aluminium and steel give us respectively mostly adhesive fracture and only adhesive fracture in all the cases for the steel, and this cannot permit us to assess the out-of-plane properties of Tensylon. Here we give a result of testing of the adhesive at 0 degrees, so pure tensile, and the response exhibits quasi-brittle fracture. This could be modeled by a bilinear adhesive, bilinear cohesive zone model. The experimental data were used to identify a bilinear cohesive zone model, and we can see that the good reproducibility of the experimental test is obtained. Concerning the Archon results, we can see a good reproducibility in terms of ultimate load. This bit of the important inhomogeneity of Tensylon concerning the 90 degree. Natively, we have two tests, but here we can show only one result. Given that we failed to record the second one by DXC, but we were able to recuperate the ultimate load thanks to the load cell of the machine. It's the only data needed to construct the envelope, the failure envelope of Tensylon. This envelope is constructed by using the data obtained from Archon testings. This envelope can give us the information concerning the stress threshold of Tensylon in its out-of-plane direction. Here we give some conclusions on the work. Tensylon is mechanically characterized, and the numerical validation is proposed for the case of 0.1 mm per minute. ABS is selected as substrate and Permabond TIA 4610 as adhesive. The combination is found as the best to achieve the out-of-plane characterization of Tensylon. The adhesive behavior is numerically validated by means of cohesive zone model, and out-of-plane properties of Tensylon are successfully characterized. TRAF, the modified Archon test, and its failure envelope is determined. Some outlooks for the work. Numerical validation will be proposed by taking into account the delamination of Tensylon, and the comparison will be done between quasi-static response of the Tensylon and its dynamic behavior from stress threshold point of view. Thank you for attention. For more information or question, feel free to contact me. Thank you again.